I know I'm going to torment you with that because as long as you don't, it's not your instant impulse, then I'm going to torment you with it, okay? If everybody had said the set containing 0, then I would have been satisfied that you are on top of that. Okay, right. Oh, and what is 1z, by the way? Z, okay, and not the set containing z, which has only one element in it. Okay, you get the idea. All right. Okay, are there any questions about this particular fact here? You're going to have to prove some things about these particular sets, including, for example, when is AZ contained in BZ? So you will get a very explicit statement about that, and that would explain my comments earlier about showing this is an A squared Z. Okay, so we have only 5 minutes left, so I think the best thing to do right now is to not to let you go, okay? I know that was the first thing that sprang into your mind, but no. I want to talk about greatest common divisor a little bit, which is something we'll have to cover in detail last time. And again, you probably learned about this, right? You probably had to do GCD of, 10 and 15, right? Which is 5, right? Okay. And how do you do that mentally? You kind of factor both those guys, right? And this is 2 times 5, and this one is 3 times 5. And so 5 is the greatest thing that divides those two, right? Okay. So what you probably have learned before is that if m and n are natural numbers, okay, you probably didn't consider what happened with integers. Greatest common divisor for mn is the greatest, or the largest, let's just say that, largest natural number that divides m and n. Well, first question you have to ask is, how do you know there is such a thing? Well, there is always a divisor, but how do you know there's a greatest common divisor? So 1 divides everything, so 1 is a common divisor. So there is a common divisor. How do you know there's a greatest one? Maybe they're divisors that get bigger and bigger and bigger, right? Yeah, we had a lemma back at the beginning. A divisor, for natural numbers, divisor has to be less than or equal to. Okay, so I got the 2 parts from that corner back there. First part is there is a common divisor, which is always 1, right? And there's a greatest common divisor by the first lemma that we proved, which was that if something divides something else, then the divisor is less than or equal to. Again, in the setting of the natural numbers. Now, there's actually a more important property, which probably you didn't learn about. And that is that if D equals greatest common divisor of mn, then D is equal to AM plus BN for some integers m and n. In fact, this is actually going to imply that. So these two things are equivalent. Okay, can everybody see that? No? Okay. So the property is that D equals AM plus BN for some integers A and B. Okay, now when I first saw this, I thought, what? I mean, why should there even be a divisor, a common divisor, that is in that particular form? First of all, why should there even exist one? Second of all, why does that somehow magically become the greatest common divisor, right? And third, why do I care? Okay, and we'll kind of address those in that order. Next time, what we're going to do is we're going to show that there is a divisor of this form, that this is going to be the greatest common divisor, although we're going to actually work in the integers instead of just the natural numbers. And that will get us the greatest common divisor. And then we're going to look at why on earth this, as it says, actually a more important property. Notice this has nothing to do with ordering at all, right? Greatest, least, okay, is kind of sort of miraculous that it ends up being greatest, okay? But this is a purely algebraic property. So if you don't have an ordering, and often you don't, you can still talk about something like this, right, without even being able to say greater or less than. But also it has kind of important applications to things like prime decomposition, which is what you all did mentally when you answered this question here, right? You broke it up into a product of primes. And these are all things that we are going to, most of which, I'm not sure if we're going to be able to get into the proof of existence and uniqueness of prime decompositions, right? That's kind of long, and we'll see how things go, okay? But certainly we'll do some things like division algorithm with this, okay? So I will see you guys on Wednesday for the